So, following Landau and Lifshitz, we have introduced pseudo-tensor, energy momentum tensor for gravity, T mu. To understand deeper its physical meaning, let us consider gravitational field in weak field approximation. So it means that we consider the following situation, that the metric tensor is approximately Minkowskian tensor plus small perturbation on top of it. Small means that all the contributions to this guy are much less than 1. In principle, what are we going to say can be done on top of any background metric, but for simplicity and for illustrative reasons, we consider, in these lectures, we consider perturbations over the flat background. So we choose as a background Minkowski metric. So we're going to restrict, at first we're going to restrict ourselves to the linear order in this quantity. At linear order in this quantity, we want to find the inverse metric tensor. To find the inverse metric tensor, we have to solve the following equation. G alpha nu equals to delta nu mu. And at linear order, we have to solve it for this. At linear order, this quantity, G mu nu, is approximately equivalent to at mu nu minus h mu nu. Throughout the rest of the lecture, we assume that the highering and lowering of the indices is done with the use of the background metric. So it means that h mu nu is, by definition, is at mu alpha, h alpha nu. So we high and lower index with the Minkowskian background metric. So with the same precision, then modulus of the determinant of the metric is approximately equivalent to 1 plus h, where h is by definition is a trace of this tensor mu nu. So as follows from the generic infinitesimal transformation, the generic infinitesimal coordinate transformation is as follows. As we remember, it is defined with the covariant derivative like this. So, and in the linearized approximation, one can see that from this and this, h mu nu bar of x is approximately h mu nu of x plus short derivative in the linearized approximation. So, in the same approximation, Christoffel symbols are as follows, are defined like this, using all this. Gamma mu nu alpha, it's approximately 1/2 eta mu beta d nu h alpha beta plus d alpha h beta nu minus d beta h nu alpha. So we see that it is linear in h. Gamma is linear in h. As a result, we remember that in Riemann tensor or in Ricci tensor, there are contributions which are d gamma and gamma squared, schematically. So these terms are of the second order in h. So at linear order, we drop them off. And as a result, Riemann tensor in the linear approximation, is as follows. It's mu nu alpha beta. Well, it's eta mu gamma d alpha gamma gamma nu beta minus, so we keep only these terms, that's what we write, minus d beta gamma gamma nu alpha. So it's approximate relation. No, at the first approximation, it's a definition of the first linear approximation for the Riemann tensor. So this is equivalent to 1/2 d nu d alpha h mu beta plus d mu d beta h nu alpha minus d mu d alpha h nu beta minus d nu d beta h mu alpha. So we are working in the linearized approximation and consider perturbations over the flat background metric. And we have written in the linearized approximation expression for the Riemann tensor. Now for the expression that follows for the Ricci tensor, which follows from that expression for the Riemann tensor, is as follows. So it's alpha mu beta nu, and this is approximately equal to (1/2) minus box h mu nu plus d nu d alpha h alpha mu plus d mu d alpha h alpha nu minus d mu d nu h. H is a trace of h alpha beta. And the box is just the D'Alembert operator. So it's at alpha beta d alpha d beta. So using the transformation that h mu nu transforms like this, d mu epsilon nu. Using this transformation, one can fix the following gauge. One can adjust h mu nu, or fix the gauge, which is as follows: d mu psi mu nu equals to 0, where psi mu nu is equal to h mu nu minus 1/2 delta mu nu h. In fact, well, this is by definition. In fact, under such a transformation, this quantity transforms like this: d mu. Well, let me write with upper index. D mu psi bar mu nu is equal to d mu. Well, by definition, it's just h bar mu nu minus d nu 1/2 d nu h bar, and this is just d mu psi mu nu plus box epsilon nu, this epsilon nu. So we can always adjust this quantity such that it will cancel this and to put this to 0. This can be done up to homogeneous, up to such epsilon which solves the homogeneous equation. Up to this equation we can always, and the remaining freedom after fixing this gauge is the same transformation like this with epsilon 0, which solves this equation. So in this gauge, it is not hard to see that in this gauge r mu nu, well, if we use this gauge here, it's a straightforward calculation. R mu nu is just 1/2 box h mu nu. Very simple. As a result, Einstein equations acquire the following form. It's minus box psi mu, this psi, is equal to 16 pi kappa t mu plus terms which are of the second order in H. So at linear order we have this equation and this comes from the second order. To find these terms, we have to redo all these calculations to the second order. Well, let's see what happens. Well, at the second order, we have the following situation, that if we use this, and then the tensor with upper indices at the second order, it's eta mu nu minus h mu nu plus h mu alpha h alpha nu. Also, modulus of g at this order is approximately 1 plus h plus 1/2 h squared minus 1/2 h mu nu h nu mu. All in all, we can do, well, this is at the second order. Now one can find also the Ricci scalar, Ricci tensor. Ricci tensor in this approximation and the second order, to the second order, looks quite tedious, but it is like this. It's 1/2 h rho sigma d mu d nu h rho sigma minus h rho sigma d rho d mu h nu alpha and symmetrized over the indices mu and nu plus 1/4 of d mu h rho sigma d nu h rho sigma plus remaining terms are also quite tedious. I hope we will fit into the board. So it's d sigma h rho nu times d rho h d sigma h rho nu anti-symmetrized over this indices plus 1/2 d sigma h rho sigma d rho h mu nu minus 1/4 d rho h mu nu d rho of h, and finally minus d sigma h rho sigma minus 1/2 d rho of h times d mu h nu rho symmetrized. So this is a Riemann Ricci scalar at the second order. To find these terms, one has to bear in mind that these terms are approximately the following. So Ricci tensor to the second order minus 1/2 eta mu nu times r to the second order minus 1/2 h mu nu times Ricci scalar to the first order. After straightforward by tedious calculation, one can find that this quantity coincides with modulus with 16 pi kappa times T mu as calculated from the expression that we have written for this formula, for this quantity. Before in this lecture we had an expression for this quantity. If we substitute into that expression this and do the calculation at the second order, this will coincide with this expression, with the second order here, with the second order in h squared here. So the meaning of this quantity is actually that it is nonlinear part. If we consider linearized perturbations and expand in powers of h, this is nonlinear part in h, so it can be attributed to the right-hand side of the Einstein equations. So now one can easily understand the reason why this quantity cannot be made tensorial. You see, in the gravity, to specify what means energy flux, so the flux through some distant surface, we have to first fix this surface. To fix this surface, we have to fix a background. So we have to have a background and consider perturbations over this background which carry the flux through that surface. So we have to consider background and perturbations. But this separation on what means background and what means perturbations changes. If we have a coordinate transformation, these terms mix under arbitrary non-infinitesimal coordinate, not necessarily infinitesimal, not linearized, not such transformation, but generic. We make a transformation, then we have to separate again what means background and what means perturbations. And this separation is ambiguous, and that's a reason this quantity doesn't have tensorial properties. And finally, one can see that under these transformations, this quantity transforms as a tensor under such linearized transformations.